Hello, in this video I will talk about the probability distribution of random variables. We'll start with the discrete random variables. So the probability distribution of a discrete random variable is simply the probability associated with each of the possible values that the random variable can take. So if x is a random variable with values x1, x2, x3, etc., then the probability that the random variable will take value xk, if we denote that as f of xk, then the probability distribution fx of x is simply the probability that random variable x will take a value small x. And small x can be anything between minus infinity to plus infinity. And if small x is not one of the values that the random variable capital X can take, then the probability is 0, so fx of x is 0. The probability distribution for a discrete random variable is also called probability mass function. You'll come across this term more often for discrete random variables. So the rules for any function to be a probability mass function are very simple. The first condition is that the probability, of course, has to be greater than or equal to 0. And sum of all the PMFs for a given random variable has to be 1. And the PMF should be equal to the probability that the random variable capital X takes a value X. This is straight from the definition of PMF. Let's look at an example of tossing two fair coins. So what is the PMF for the random variable capital X if it counts the number of heads in the experiment? So the 4 outcomes are listed in the table, and the number of heads denoted by capital X, the random variable, can be between 0 to 2. And to find the PMF of the random variable X, we need to calculate the probability of each of these possible outcomes. So if you consider the outcome of 2 heads in the 2 coin toss, and since both the coins are fair coins, we can easily calculate the probability of head and head as 1 over 4. It's the same for all the other combination for this 2 coin toss experiment. But the PMF talks about the probability of the random variable X taking a particular value. So here X can be 0, 1 or 2. So the PMF is given by the probability of random variable X taking a value 0, which is 0.25, probability of X taking a value 1. There are two possibilities, so we combine these two probabilities and you get 0.5. And the probability of X taking a value 2 is 0.25. And the PMF is 0 for all other values. Another way of describing the distribution of a random variable is cumulative distribution function, or CDF. It can be used for both continuous and discrete random variables. It's more often used for the continuous random variable, but you might see examples where CDF are also used for discrete random variables. So the CDF is defined for values of the random variable that are less than or equal to a constant. So we can assign a probability to this event that the random variable takes a value less than or equal to some small x. And this probability is denoted by capital F of x, and that is called the CDF. So mathematically, f of x is the probability that the random variable is less than or equal to small x for all possible values of small x. So let's look at some properties of CDF. So capital X is the random variable, and small x can be anything between minus infinity to plus infinity. So let's start from the two extremes. If small x is plus infinity, then the probability that the random variable is less than or equal to x or infinity is 1, because all possible values of random variable will be less than or equal to plus infinity. Similarly, at the other extreme, the random variable capital X taking a value less than or equal to minus infinity is going to be 0, because that's an impossible event. The random variable cannot take a value less than minus infinity. So those are the two properties. The third one talks about probability of the random variable lying between two constants a and b. This can be written as f of b minus f of a. We can explain this on this diagram where b is greater than or equal to a. So f of b is everything less than b. So the random variable x is taking values less than b. So to get the number, the probability between a and b, we simply subtract the CDF at a from the CDF at b. Another important property of the CDF is it's a non-decreasing function. So what does this mean? So if x increases, if you move to the right, then the probability that the random variable capital X is less than or equal to x is going to increase, because you have a larger area to the left of small x. So as x increases, the probability is going to increase. So this, for a discrete random variable, the CDF might look like a staircase. So we've looked at the probability mass function and the cumulative distributive function for a random variable that is discrete. And we can easily convert between the two. So if we know the PMF, we can calculate the CDF and vice versa. I'll take this example to explain. So let's say we know the PMF of the random variable, which is the probability of x is equal to some constant. So in this example, probability of 0 is 0.1, probability of 1 is 0.2, and so on. So this is the PMF of the random variable. Now if we want to calculate the CDF from here, we simply accumulate the PMF. So probability of x less than or equal to 0 is going to be the probability of x is equal to 0, because everything below 0, the PMF is non-existence or 0. So the CDF at 0 is the probability 0.1, so you have 0.1. Now the CDF at 1 is the probability of x less than or equal to 1, so you can add these two numbers. So probability of x is equal to 1 and probability of x is equal to 0. So this goes to 0.3, 0.1 plus 0.2. Similarly, the CDF at x is equal to 2 or less than or is equal to 2 is going to be the probability of x equal to 2, probability of x is equal to 1, and probability of x is equal to 0. So by combining or adding those three probabilities, we get the CDF at 2, and so on. So keep in mind that f of x is going to be 1 when it covers all the possible values that a random variable can take. This is straight from the definition. So mathematically, we can write f of x, capital F of x, that's the CDF, in terms of the PDF using the summation. Similarly, if we want to go from the CDF to the PMF, we have to subtract. So if we want to get the PMF at 3, we subtract CDF f of 3 minus f of 2, and so on. So mathematically you can write it as this function. Let's take a look at the coin toss example again. So we have the outcomes and we have the values the random variable x can take, which is the number of heads in this experiment. So the PMF of x is simply the probability that the random variable x takes value between 0 and 2. So probability of x is equal to 0 is 0.25, probability of x is equal to 1 is 0.5, probability of x is equal to 2 is 0.25. And the CDF of x, let's calculate that. So at 0, f of 0 is probability of capital X less than or equal to 0. The only possible value is 0, so it's going to be 0.25. F of 1 is probability that the random variable takes values less than or equal to 1, which will be probability of x is equal to 1 and probability of x is equal to 0. So we combine these two. The probability of CDF at 2 is probability of capital X less than or equal to 2, which is the sum of all three. So it's 1. So we can show that in a plot as well. So as we have mentioned before, the CDF is usually a staircase. So the CDF at 0 is 1 by 4, CDF at 1 is 3 over 4, and CDF at 2 is 1. Here is an example of the Bernoulli distribution, which is the simplest discrete random variable, and we have come across this before. For example, a single coin toss. So a random variable is said to have a Bernoulli distribution if the random variable takes only values 0 and 1, such that the probability of x is equal to 1 is some value p between 0 and 1, and the probability that x takes the value 0 is 1 minus p. An indicator random variable has the Bernoulli distribution because the indicator random variable can take only values 0 and 1. Many times x, the random variable, if it is a Bernoulli distribution, then in shorthand it can be noted as this, with the probability p for the random variable x to take value 1. We can easily calculate the CDF of the random variable because we know the PMF. So it will be 1 minus p at x is equal to 0. So the CDF at 0 is 1 minus p, and the CDF at 1 is going to be 1 because it will be the sum of p and 1 minus p. Now let's look at the distribution function of continuous random variables. The CDF, as I mentioned before, is more commonly used for continuous random variables, and the definition of CDF is the same for both continuous and discrete. So this information is applicable for both discrete and continuous random variables. The properties are also the same. The only difference is x can be any continuous value, small x, instead of in the discrete case where it used to be discrete values or countable values. The other properties apply for continuous random variables similar to the discrete random variable. Coming to the probability distribution function, or what we call PMF for discrete random variables, the difference between continuous and discrete random variable is that the probability of x is equal to some constant is going to be 0 for the continuous case. So if you look at an example, let's say x is a random variable that takes on the value of a person's height, then the probability of x is exactly equal to, let's say, 68 inches is going to be 0. However, the probability that x takes a number between 67 to 68.5, for example, is greater than or equal to 0. So because of this reason, we cannot have a tabular form for the probability density function in the case of continuous random variable. So instead, for the continuous case, we define it as a density. So to get the probability, you have to multiply the density by certain length. The PDF of a random variable which is continuous is denoted by the same small f of x, and the properties are similar. So f of x is going to be greater than or equal to 0 for all values of small x. So f of x cannot be negative. It's a density. And the sum integration of f of x over all possible values of x is going to be 1. And if you want to calculate the probability that the random variable takes a value between a and b, we simply integrate the PDF between the limits a and b. So if a and b are very close to each other, then we can say that the probability of the random variable taking values between a and b is going to be f of x times the length. Similar to the discrete case, we can easily convert between PDF and the CDF. So the formulas are given here. If we know the PDF, then the CDF can be calculated by simply integrating the PDF between -infinity to x. And to go from the CDF to PDF, we simply differentiate the CDF. So instead of summation and difference in the case of discrete, for the continuous case we have integration and differentiation. So that brings us to the end of this video. In this video we covered the probability distribution for the discrete random variable and the continuous random variable. Thank you.